Okay, so we have finally reached to the last subtopic of ODE. So this is going to be the last subchapter for this whole course, so which is called as the half-range Fourier series. The Fourier series that we have discussed before in 4.3, so that is known as the full range Fourier series, and this one is known as the half-range. So before I start with the calculations, start with like how do you sketch the graph and so on. First of all, I would like to explain to you what is the difference between the full range and the half-range. Okay, the difference is that for the case of full range, you are being given a function f of t, and the function f of t is a periodic function. So what you're going to do is you're going to sketch the periodic function. So from the sketching, you decide that whether your function is odd, even, or neither. Remember, when you have an odd function, a0 and an are both going to be 0. Even bn is going to be 0. And for the case of neither, it's bad news. You have to calculate all the Fourier coefficients. Okay, and then after you have got the Fourier coefficient, then you're going to write them as the Fourier series. So that will be the case of periodic function. And before I start with the half range, and I would like to highlight one thing to you. So the fact that the Fourier series, it can only exist for periodic function. If the function is not periodic, then Fourier series doesn't exist as well. Okay, so that is why for the case of half range, what happened is that you are being given a function f of t. So previously it's f of t as well, so this is f of t as well. But what is the major difference? The major difference is that for the case of half range, the function f of t given is not periodic. And remember what I mentioned just now. So if it's not periodic, meaning by you cannot find the Fourier series. And there will be an extra information given as well. So the extra information given is that the question is going to ask you whether it wants sine series or cosine series. So based on the non-periodic function given, the f of t given, and knowing whether your function is supposed to be sine series or cosine series, you are going to come out with a periodic function. Okay, so the first step is going to be different from full range and half range. Okay, so for half range, the first step is you will be converting a non-periodic function to a periodic function. So that will be the first step. Okay, the periodic function is now no longer going to be f of t, so it's going to be called as a new function. So we call that as f star t. And after you have obtained the periodic function, then only you can find the Fourier series, because now it's periodic, then only the Fourier series exists. So meaning by the only difference for the case of half range and full range is that for full range, the function given is already periodic, but for half range, you are given a function that is not periodic, so you convert that to a periodic function. Okay, so before I start with what I'm going to do in this particular video is mainly I want to show you how do we convert a function that is not periodic to a periodic function. I'm going to show you how do I convert from f of t to f star t, but before that, I'm going to explain to you, so what is it about sine series and cosine series? So this is going to be a very important features, because whether the question wants sine series or cosine series, so that is going to determine your calculation. So whether it's going to be a calculation for odd or it's going to be calculation for even function. Okay, however, so if you already understand the calculation for full range in the previous subtopic, you would have no problem with this subtopic as well. The calculation is the same, only the first step will be different. Okay, let's see why is it about sine series and cosine series. But first of all, so let me write down the Fourier series formula. Okay, so this will be the formula. So Fourier series f of t is given by a half a0 plus sum of n from n equal 1 to infinity of a n cos of n omega t plus sum from n equal 1 to infinity of bn sine of n omega t. So that will be the formula. Okay, but now the only difference is that for the case of half range, so our function is no longer ft, our periodic function is going to be called as f star t. So our Fourier series is also going to be on f star t. Okay, there are going to be two types of half range sine series. So this one, the first one is called as two type of half range Fourier series. So the first type is called as the sine series. Okay, so this is going to be the first type. Okay, why is it about sine series? So if you have a look at the coefficients over here, So when you have an is going to be multiplied by cos of n omega t. So if you have an, automatically your answer is going to be in terms of sum of cosine. And if you have bn is not equal 0, automatically there will be sine is in your function. So that is where this sine series and cosine series comes from. Okay, what happens is that when you have a sine series, so your Fourier series only consists of sine terms. So where are the sine terms? So the sine terms come from here. So meaning by your Fourier series f star t, let me use black pen for this. So your Fourier series f star t only consists of the sine terms which come from the bn right here. So it's going to be sum from n equal 1 to infinity of bn sine of n omega t. So that is why it is called as the sine series, because everything is going to be in terms of sine. There will be no cosine terms in your Fourier series. Okay, and what happens is that it is only this series over here is only achievable when we have that a0 and an, both of them are going to equal 0. Then only our series is going to become and looks like this. Okay, and we know that an, so the formula is given by 2 over t. The integral is going to be from d until d plus t. So remember, our periodic function is given by f star t now. So f star t, so cos of n omega t dt. Okay, the formula for full range and half range is exactly the same. The only difference is that now, instead of using f, our function is f star t. Okay, and we know that for this case, when it is a sine series, so this whole term over here, an, the integration is going to equal 0. And we know that this integral is going to become 0 if the product of this is going to be 0 if product is odd. Okay, so meaning that when I multiply f star t and the cosine, so it's going to be odd, then only the integral will become 0. Okay, what happens is that we know about cosine. Cosine is always an even function. Okay, and what happened is that, so when we multiply f star t with an even function, it become odd. So what is being multiplied by even, that is going to give you an odd function. So automatically we can only achieve odd function as the product when we multiply even and with an odd function. Automatically, therefore, for this case, so this is going to be an odd function, because odd and even, then only the whole thing is become odd. So therefore, for the case of sine series, so let me put a paper over here. So therefore, for sine series, okay, so f star t is going to be an odd function. Okay, so that is always the case when you have sine series. Remember, when you have sine series in mind, so it is always going to be, your periodic function is supposed to be odd. Okay, so that is going to be about sine series. So now let's have a look at the cosine series. So it's going to be pretty much the same argument though. Okay, so now it's going to be cosine series, and here this is going to be our general Fourier series, and now it's going to be the other way around. So cosine series means that we don't have any sine terms in there. Everything is going to be in terms of cos. And remember, a0 and an, they come in pair. When an is not equal 0, so that when an exists in the first series, a0 is going to exist as well. So that is why for this case, our Fourier series f star t, so it's going to be given by a half a0 plus sum from n equal 1 to infinity of an cos of n omega t. So that is going to be the cosine series. And we're going to use the same argument. And this here is only achievable when our bn is equal 0. So that is why we don't have any sine terms. And everything is going to be in terms of cosine, because bn is equal 0. So cosine terms mean that everything is going to be in terms of cosine. And we know the formula for bn. So bn is given by 2 over t. So the integral from d until d plus t. So f star t, so sine of n omega t dt. And it is going to equal 0 for this case. So I'm going to use the same argument. So the fact that it's going to become 0 when the product of both of this is going to be odd. So product is odd. And we already know about sine. So sine is always an odd function, and here when we multiply this with an odd function, it becomes even. So that must have been the case that f star t is an even function. So that is why. So therefore, for cosine series, okay, so f star t is even. Alright, so now I want you to bear this in mind. So the fact that when you have sine series, okay, your periodic function is supposed to be an odd function, and when you have a cosine series, so your periodic function is supposed to be even. Why? Because of this argument that I've explained to you right here. Okay, so based on knowing that, then only we can find our function f star t. Then only we can transform from f star t to ft to f star t. So here, so this is my function. So I've been given a function f of t is equal to t plus 1 from -1 to 0. So here, this is not a periodic function. So because we have no information about the period value. So therefore, this function over here is not periodic. And we're going to change that to f star t. Now, f star t is going to be the periodic function. So how do we know what kind of function is this going to be from here? We have been given in the question, we're going to sketch the web form. This is going to be the range. So it's going to be from -1 until 5. For what? For half-range Fourier cosine series. And from what I have explained to you previously, when we have a cosine series, so the periodic function is supposed to be even. So that is what we're going to do. We're going to come out with a periodic function that is even. So let me put the scale first. So -1, 1, 2, 3, 4, let's say 5 is somewhere over here. Actually, I don't need it until 5. Okay, and this is going to be the analytical description. So what we're going to do is first we're going to sketch the function, and then we're going to write down the analytical description. So in case that you still don't know what is analytical description, so the idea is going to be like this. So if I have a function and I sketch the graph, for example, it looks like this. So this is called as the graphical description. So I describe the function graphically. It is known as the graphical description. But if I were to represent the function in terms of an equation, for example, I write that f of t is going to equal t. So then this equation right here is called as an analytical description. I describe the function analytically. So it's called as analytical description. It's just basically just the equation. So now let's get back to this. So now I'm going to sketch this function first. F of t is going to equal t plus 1 from -1 to 0. I'm going to use the same trick as I've done previously. Pick the lowest and the highest value. So when t is equal -1, when I substitute my value of t right there, I'll end up with a 0. And when t is equal 0, so my function f of t, that is going to equal 1. So the coordinate is going to be -1, 0. It's going to be right here. And 0, 1. So let's say 1 is somewhere up here. And because this is t to the power of 1, it's supposed to be a linear function, a linear graph. So that's how it looks like. Okay, now, this is going to be half of how my cycle looks like. Okay. What do I mean by half of the cycle? So meaning that the full cycle is going to be from -1 until 1. So that is going to be my full cycle. Because remember, -1 to 0, that is a half. That is why it is called as a half range. And now I'm going to come up with how the other graph looks like. And how do I know how the other half looks like? From knowing that the graph is supposed to be even. And I did mention this to you before. When we have an even function, so it's going to be side by side your vertical axis. So that is going to be sort of like a mirror for you. So that is where you reflect your function. And of course, this function over here. And if I were to reflect this function with the vertical axis, with the f star t axis as being the mirror, so the other half of the graph is going to look like this. You're going to reflect that on the vertical axis. Okay, and this is going to be my even function. And of course, for this case, what is the period value? So it covers from -1 until 1. So the period value is going to equal 2. Okay, so for now that I have the shape, how does the periodic function is supposed to look like, I can now write down the analytical description, f star t. Okay, so my first function is going to cover the first line. So the first line covers from -1 until 0. And, no, that is the wrong notation. So it covers from -1 until 0. And the second line, it covers from 0 until 1. Okay, so we have 2 lines, 2 functions. Okay, the first function, remember the equation of y equal mx plus c. So I've been repeating this to you times already. So now our y is our function f star t. Okay, and x is now being replaced by a variable t, but other than that, it remains the same. Okay, for this case, we have an equation of t plus 1, so meaning by our m value, so that is going to equal 1, and that is actually being, the evidence is being supported by this line right here, that we can see that as the value of x increase, so the graph is going up. But if you have a look on the other side, what happens is that this line, as the value of t increase, so the line is actually going down. So that is why when you have an even function, so what happens is that the gradient is going to be the opposite. So when on the other side is m equal 1, automatically on this side my value of m is going to equal negative of 1. And how about the c value? The intercept is the same, so they share the same intersection, which is going to be here, and my c value is going to equal 1. So therefore for this case, remember, my m value is going to equal negative 1 and my c value is going to equal 1. I'm just going to substitute into this equation. So this is where the value of m is going to be substituted, and this is where I'm going to substitute the value of c. So that is why when I write my equation, so I'm going to end up with this one. I'm just going to copy it down from here. So it's going to be t plus 1 from negative 1 until 0. And on the other side, my m value is going to equal negative 1. So I'm going to have negative 1 of t. And my c value is going to equal 1. So I'm going to have plus 1. So that is going to be my equation. So negative t plus 1. It is always the case. When you have an even function, so your gradient is going to be the opposite. If this side is m equal 1, on the other side is going to be m equal negative 1, and so on. The positive and negative is going to be different. And of course, remember, if it's a periodic function, you need to provide the information about the period value. And we know for this case, the period value is going to equal 2. So therefore, I'm going to have another information right here. F star t is going to equal f star of t plus 2. So that is going to be my analytical description. So this analytical description is going to give you at most 3 marks, at least 2 marks. And sketching will give you 3 marks. So that is already 5 marks altogether just for doing this for half range. Okay, but do not leave your function like this. You're not done yet. You have to fill it in here from negative 1 until 5. And we know that because the period value is equal to, so I am going to have another 2 cycles. So this is going to be the second cycle, and this is going to be the third cycle. So that is how my function looks like. Okay, so that is going to be the first one, half range Fourier series. And we started with a not periodic, with a function that is not periodic, and now we come out with a periodic function. So that is what you're supposed to do. Step number 1. We haven't done the calculation yet. This is just step number 1 of half range. Right, so I'm going to show you another example. And now, so this is going to be for the case of half range Fourier sine series. And we know that if it's a sine series, because of the arguments that I have explained to you previously, so your graph is supposed to be an odd function. Okay, now I'm going to sketch my graph, and it's going to cover from negative 3 pi until 3 pi. So let me put the scale on the axis first. So I'm going to have pi, 2 pi, and 3 pi. On the other side is going to be negative pi, negative 2 pi, and negative 3 pi. Okay, now I'm going to start by sketching this, 0 and pi. Okay, I'm going to substitute this t right there. Right, so when I substitute t equals 0, I'll end up with a pi. So 0 pi is going to be somewhere over here, 0 and pi. So let's say this is going to be a pi value. That's my 0 pi. And when I substitute t equal pi in here, I'm going to have negative pi plus pi. That's a 0. Pi 0 is going to be somewhere here. And again, this is t to the power of 1. So it's going to be a straight line. So this is how my graph looks like. How half of my function looks like. Okay, now this is supposed to be an odd function, as I have explained to you in 4.2 when we discussed about even, odd, and neither function. So the features of an odd function is that when you have half of the line, so half of the function, how do you get the other half? You have to reflect that twice on both axes. So that's what I'm going to do. So now where are going to be my axis? I'm going to reflect that both on the horizontal axis and also on the vertical axis. So it doesn't matter which one you start with. You can always start first with the vertical, then horizontal, and the vertical. So no matter which axis you start first, it's always going to give you the same shape. Alright, so let's say I'm going to start with the horizontal axis first. So if I were to reflect this on the horizontal axis. So this is how my line is going to look like. And now if I were to reflect that again on the vertical axis, so this is going to be the line. Okay, so now I don't need the reflection over here, so I'm just going to delete that. So this is going to be my pi. Alright, so I reflect it twice on both axes. Because this is supposed to be symmetrical, if the top over there is pi, so this is going to be negative of pi. Remember, because the two lines, they are symmetrical. They are the same line that is being reflected. Alright, so now that I have the shape, I can now write down the analytical description. So my analytical description is going to be for function f star t. Again, I have two lines, so meaning that I'm going to have two functions. So the first one is going to cover from negative pi until 0. And the second line is going to cover from 0 until pi. But the thing is that the line from 0 until pi is already given up here. So I just copy it down. It's going to be negative t plus pi. And if you have a look at what's going on right here, so this graph, it's going down. So how do you know it's going down or going up? It's going to be like for this direction. So the value of t is increasing. So what happened to the value of y? Is it going up or going down? So for this case, we know that this m value, this is negative 1t. So the m value is equal negative 1. So here m is equal negative 1. And the feature when you have an odd function is that your both two lines, they are going to be parallel. If that is m equal negative 1, so this reflected line is also m equal negative of 1. But the c value will be different. So here my c value is going to equal pi, but my second line, it intercepts at negative of pi. So that is why when I substitute into this equation right here, this particular equation, the value of m and c, so I will end up with a function of negative m is negative 1 multiplied by t, and my c value is going to equal pi. So I'm going to have negative t minus pi from negative pi until 0. And again, so for the case of the period, so I'm going to, this is going to be the period value, alright? So here it covers from negative pi until pi, so that is a distance of 2 pi. So here we can write that f star t, so that is going to equal f star of t plus 2 pi. Okay, so that is going to be the period information. And of course, do not leave your function like this, so fill it in. So here our range is going to cover from negative 3 pi to 3 pi, so covers that everywhere. So let me sketch that. So on this side, I'm going to have one cycle down and up. On the other side, I also going to have another cycle down and up here. So that is roughly how my function is going to look like. Okay, so remember, this is already like 6 marks for you already, 3 and 3, that's right. So this is already 6 marks. So this is, and 6 is definitely going to be a lot of marks. And remember, if you write your function wrongly for this one, automatically it's going to affect your calculation. Your calculation is going to be wrong as well. Okay, so be careful with this. So when you have an odd function, so the two lines are going to be parallel, they're going to have the same gradient. And what happens is that when you have an even function, so the two lines are going to be the opposite, and they are going to have the difference between of the sign of being positive and negative. Okay, so that is going to be the first step of half range, so converting a non-periodic function to a periodic function. So I'm just doing this part right there. Okay, so next I'm going to show you in the example and how do you proceed with the Fourier series. Alright, so I'll see you in